To the dielectric 9. Return now to the consideration of electrostatics. We are to regard ourselves as living immersed in an infinite, all-permeating ocean of perfect, incompressible fluid or liquid, as fish live in the sea. But this is not all, for if that were our actual state, we should have no more notion of the existence of the liquid than deep-sea fish have of the medium they swim in. If matter were all perfectly conducting, such would be our state. In a perfectly free ocean, there is no insulation, no obstruction to flow of liquid. It is the fact of insulation that renders electrostatics possible. We could obstruct the flow and store up definite quantities of a fluid in which we were totally submerged by the use of closed vessels, of course. But how could we pump liquid from one into another so as to charge one positively and another negatively? Only by having the walls elastic, by the use of elastic bags and elastic partitions across pipes. And so we can represent a continuous insulating medium, like the atmosphere or space, by the analogy of a jelly, through which liquid can flow only by reason of cracks and channels and cavities. Modify the idea of an infinite ocean of liquid into that of an infinite jelly or elastic substance in which the liquid is entangled and through which it cannot penetrate without violence and disruption, and you have a crude model of the general insulating atmosphere. Our ocean of fluid is not free and mobile like water. It is stiff and entangled like jelly. Nevertheless, bodies can move through it freely. Yes, bodies can. It is the liquid itself only which is entangled. It is not easy to picture freely and naturally the motion of ordinary matter through the insulating medium of space, unless we step beyond our jelly analogy to the more refined and truer theory of the vortex sponge of perfect liquid. But it is characteristic of analogies to break down when pressed too far, though they are useful up to a certain point. Insulators being like elastic partitions, or impervious but yielding masses, conductors are like cavities, or rather like porous or spongy bodies, perfectly pervious, though with more or less frictional resistance to the flow of liquids through them. Thus, whereas bodies easily penetrable by matter are impervious to electricity, bodies like metals, which resist entirely the passage of matter, are quite permeable to electricity. It is this inversion of ordinary ideas of penetrability that constitutes a small difficulty at the beginning of the subject. However, supposing it overcome, let us think of the ordinary lecture table assemblage of insulated spheres and cylinders connected by copper wire as so many cavities and tubes in an otherwise continuous elastic impervious medium, which surrounds them and us and extends throughout space wherever conductors are not. All, however, cavities as well as the rest of the medium, being completely full of the universal fluid. The fluid which is entangled in insulators is free to move in conductors, whence it follows that its pressure or potential is the same in every part of a conductor in which it is stationary. For if there were any excess of pressure at any point, a flow would immediately occur until it was equalized. In an insulator, there is a tendency to equalization, but it cannot take effect. So differences of pressure are exceedingly common in insulators and are naturally accompanied by a strain of the medium. It is instructive now to think over a number of ordinary electrical experiments from this point of view, to think of the fluid as flowing freely through conductors and settling down to a state of equilibrium or uniform pressure in them. But straining insulators, as high-pressure water might strain elastic walls or boundaries, straining them even to bursting if the partitions be made too thin. 10. There have been, as you know, two ancient fluid theories of electricity, the one-fluid theory of Franklin and the two-fluid theory of Simmer and others. A great deal is to be said for both of them within a certain range. There are certainly many points on which they are hopelessly wrong and misleading, but it is their foundation on ideas of action at a distance that condemns them. It is not the fluidity. They concentrate attention upon the conductors, whereas Faraday taught us to concentrate attention on the insulating medium surrounding the conductors, the dielectric, as he termed it. This is the seat of all electrostatic phenomena. From the point of view of static electrification, conductors are mere breaks in it, interrupters of its continuity. To Faraday, the space round conductors was full of what he called lines of force, and it is his main achievement in electrostatics to have diverted our attention from the obvious and apparent to the intrinsic and essential phenomena. Let us try and seize his point of view before going further. It is certainly true as far as it goes, and is devoid of hypothesis. Take the old fundamental electric experiment of rubbing two bodies together, separating them, and exhibiting the attraction and repulsion of a pith ball, say, and how should we now describe it? Something like this. Take two insulated discs of different material, one metal, say, and one silk. Touch them together. The contact effects a transfer of electricity from the metal to the silk. Rub slightly to assist the transfer, since silk is a non-conductor, then separate. As you separate the discs, the medium between them is thrown into a state of strain, the direction of which is mapped out by drawing a set of lines called lines of force from one disc to the other, coincident with the direction of strain at every point. As Faraday remarked, the strain is as if these lines were stretched elastic threads endowed with the property of repelling each other as well as of shortening themselves. In other words, there is a tension along the lines of force and a pressure at right angles to them. When the discs are near and the lines short, they are nearly straight, figure 1. But as the distance increases, they become curved, bulging away from the common axis of the two discs, and some even curling round to the back of the disc, figure 2. Until, when the discs are infinitely distant, as many lines spring from the back of each as from its face, and we have a charged body to all intents existing in space by itself. The state of tension existing in the medium between the discs results in a tendency to bring them together again, just as if they were connected by so many elastic threads of no length when unstretched. The ends of the lines are the so-called electrifications, or charges, and the lines perpetually try to shorten and shut up so that their ends may coincide and the strain be relieved. If one of the discs touches another conducting body, some of its lines instantly leave it and go to the body. In other words, the charge is capable of transference, and the new body is urged towards the other disc, just as the disc was from which it received the lines. If this new body completely surrounds the disc, it receives the whole of its lines, and the disc can be withdrawn perfectly free and inert. This is Faraday's ice pail experiment 4. Chart 11. Now take the two charged discs facing one another, and let's say a suspended gilt pith ball hang between them. Being a conductor, there is no strain inside it, and so it acts partially as a bridge, and several of the lines pass through it, or rather, they end at one side of it and begin at the other. Thus it has opposite charges on its two faces. It is under induction, figure 3. Let it now be moved so as to touch one of the discs. The lines between it and the disc on that side have shut up, and it remains with those only which go to the other disc. Besides these, it receives, unbalanced, some of the lines which previously belonged to the touch disc. Its line of force now will pull it over to the far disc and there shut themselves up. From that disc it receives more, and it travels with them back to the first disc, and so on, figure 4, perpetually receiving lines and shutting them up, until they are all gone and the discs are discharged. The experiment is easily performed and illustrates discharge by alternate contact. This mode of stating the facts involves no hypothesis whatever. It is the simple truth. But it may at once be admitted that lines of force have no more and no less existence than have rays of light. Both are convenient modes of expression. But so long as we adhere to this mode of expression, we cannot form a complete mental picture of the actually occurring operations. In optics, it is usual to abandon rays at a certain stage and attend to waves, which we know are of the essence of the phenomenon, though we do not yet know very much about their true nature. Similarly, in electricity, at a certain point we are led to abandon lines of force and potential theories and try to conceive the actual stuff undergoing its strains and motions. It is then that we get urged towards ideas similar to those which are useful in treating the behavior of an incompressible fluid. In a much modified sense, we have still a fluid theory of electricity, and a portion of the ideas of the old theories belong to the new theory also. Thus, Franklin's view that positive charge was excess and negative charge was a deficit in a certain standard quantity of the fluid, which all bodies naturally possessed in their neutral state, remains practically true, except that we have reason to wish that he had happened to interchange the nomenclature, since it is what he called negative that turns out to be the excess. But too much confusion would result from trying to change now. His view that the fluid was never manufactured, but was taken from one body to give to another, so that one gained what the other lost, no more and no less, remains practically true. Part also, a less part, of the two-fluid theory likewise remains true, in my present opinion, Part 90, but this is not a branch of the subject on which I shall enter in the present part. It will suffice for the present to fix our attention on one fluid only. You are to think of an electric machine as a pump which, being attached to two bodies respectively, drives some electricity from the one into the other, conferring upon one a positive and upon the other a precisely equal negative charge. One of the two bodies may be the earth, in which case the charge makes little or no difference to it. But, as has been objected before, if electricity is like an incompressible and inextensible fluid, how is it possible to withdraw any of it from one body and give it to another? With rigid bodies, it is not possible, but with elastic bodies, it is easy. The act of charging a sphere is therefore analogous to pumping water into an elastic bag, or rather into a cavity in the midst of an elastic medium, whose thick walls, extending in all directions and needing a great pressure to strain them, better represent the true state of the case than does the thin boundary of a mere bag. Draw a couple of such cavities and consider fluid pumped from one into the other, and you will see that the charge, i.e., the excess or defect of fluid, resides on the outside. The interior was full and remains full. If the fluid is exactly incompressible, not the least extra quantity will be squeezed by the pressure into the space originally occupied by the cavity. This is the moral of the Cavendish experiment, paragraph 4. It proves that electricity is precisely incompressible, a fact which is further explained in paragraph 14a. You may also show that when both cavities are similarly charged, the medium is so strained that they tend to be forced apart, whereas when one is distended and the other contracted, they tend to approach. Further, you may consider two cavities side by side, pump fluid into or out of one only, and watch the effect on the other. You will thus see the phenomena of induction, the near side of the second cavity becoming oppositely charged, i.e. the walls encroaching on the cavity, the far side similarly charged, the cavity encroaching on the wall, and the pressure on the fluid in the cavity being increased or diminished in correspondence with the rise or fall of pressure in the charged or inducing cavity. In other words, conductors rise in potential when brought near a positively charged body, and their charge, if any, though not altered in quantity, becomes redistributed. The actual changes in volume necessary to the strain of these cavities are a defect in the analogy. To avoid this objection, one will have to accept a dual view of electricity, a sort of two-fluid theory, which many phenomena urge one to contemplate. For the two constituents of ether may then be sheared past each other, one increasing as the other decreases in the charged cavity, setting up a shearing strain or distortion which involves no expansion or contraction in volume and leaving the total quantity of ether everywhere unchanged. Cf. Work 18. Return circuit. Sometimes a difficulty is felt about electricity flowing in a closed circuit, as for instance in signaling to America and using the Earth as a return circuit. The question arises, how does the electricity find its way back? The difficulty is no more real than if a tube were laid to America with its two ends connected to the sea and already quite full. If now a little more seawater were pumped in at one end, an equal quantity would leave the other end, and the disturbed level of the ocean would readjust itself. Not the same identical water would return, but an equal quantity would return. That is all one says of electricity. One cannot label and identify electricity. To imitate the inductive retardation of cables, the tube should have slightly elastic walls. To imitate the speed of signaling, the water must be supposed quite incompressible, not elastic as it really is, or each pulse would take 3/4 of an hour to go, even through a perfectly rigid pipe. Knot 14a, incompressibility of electricity. The equivalence of the different modes of expression at the beginning of paragraph 4 is, I find, not obvious. it seems worthwhile to explain these fundamental matters at greater length. One of the fundamental experimental facts concerning electricity is that it is impossible to charge an insulated chamber by performing electrical experiments in its interior. Electrical machines inside a conducting chamber and electroscope outside, or vice versa, are perfectly independent of each other. This may be expressed by saying that the field of force outside a conductor and the field of force inside are quite independent, that there is entire dislocation of every line of force at the conductor, that a closed conductor acts as a perfect electrostatic screen. A second fundamental experimental fact is that if a charge be in any way communicated to, or even passed into the interior of a hollow conductor, the same precise quantity at once appears on the outside. And a variant of this is that if the outside skin of a conductor be peeled off, all charge is removed with that outer skin, no trace remaining below it. These two facts lead us to say that electricity behaves like an incompressible fluid of which all space is precisely full, a fluid, moreover, which cannot be manufactured but only moved about. For think of a closed chamber in the sea with pumps inside it. So long as there is no communication through the walls, all that the pumps could do would not result in a trace more liquid in the vessel than there was at first. The vessel cannot be thus charged. But now suppose some water to be pumped from the outside into the interior through a suitable opening. How could it be done? The vessel being already by hypothesis quite full, either the water must be compressible, in which case the extra charge would exist uniformly throughout the enclosed space, or the vessel must be expansible or porous, in which case the extra charge is not found in the original space at all, but outside it. Whatever extra quantity was pumped into the original space, that same amount precisely would instantly appear outside it, and this is what happens with electricity. In order to examine whether water is incompressible or not, we might perform this experiment. Inside a metal cavity provided with a pressure gauge, introduce a strong elastic bag and distend it by pumping water into it. Fig. 10. As the bag swells, the pressure in the outer vessel will rise unless it is continually relieved by connection to earth. Having finished pumping into the bag, close any leak the outer vessel may have had, examine the gauge carefully, and then puncture the bag inside. The water in the bag suddenly escapes from pressure, and if the slightest degree elastic, will increase the pressure in the outer rigid vessel, and thus will cause a sudden small rise of the gauge. If it be incompressible, the gauge will indicate nothing. Nothing will happen except the release of tension in the bag. The water will indicate nothing whatever, unless it had been actually compressed. This is precisely Faraday's ice pail experiment, and the result teaches us that electricity is perfectly incompressible. The Cavendish experiment, where the skin is removed from a charged conductor, which is then tested and found exactly uncharged, is another more stringent but more difficult mode of doing the same thing. If a real positive result could be got by either of these experiments, it would constitute a measure of the compressibility or volume elasticity of the ether. It would show that longitudinal thrusts, such as those of gravitation, do not exist instantaneously throughout space, but are propagated in time at a certain velocity. It is easy to see that the facts related above carry with them such mere technical expressions as that total induced charge is always equal and opposite to inducing charge, because induced charge merely represents the condition of the interior surface of a chamber into which an inducing charge has been introduced, and an equal quantity having been thereby extruded by the inner surface of the wall must have been left negatively charged by that precise amount. Furthermore, the incompressibility of electricity necessitates its flow always in a closed circuit. In most cases it is obvious, but take a case where it is not obvious. When a charge of electricity is moved from place to place, as for instance from outside to inside a room, it is not thereby piled up in the room and withdrawn from elsewhere, for an equal quantity instantly goes through the walls and appears outside. It has not been exhausted from one part of space and condensed in another. So even in this case, it has moved in a closed circuit and has behaved precisely as an incompressible fluid filling all space must behave. That is what it does, always. Thus, the equivalence of the statements at the beginning of Preceg 4 are clear.